I can't believe it's not a queue. But first, I wanted to ask if anybody's heard of the game Keep Talking and Nobody Explodes? Anybody played it? All right, so I'm going to use this game as a metaphor. It's a party game, so everybody sits around a table and enjoys this. One person acts as a diffuser, and they can see like a homemade bomb with wires and buttons. And their job is to defuse this bomb, but they don't know how. So the rest of the players are the experts, and they have a bomb defusal manual. And this manual tells them what buttons to press, what wires to cut. But they can't see the bomb. So the game is this communication between the diffusers, and the diffusers explain to the experts what the bomb looks like, and then the experts telling the diffuser what to do. So it usually looks like this, one person looking at a computer screen, and then a bunch of drunk people telling that person what to do. Now, I want you to imagine for a second that instead of just talking to each other across the table, that the experts have to communicate to the diffuser by talking through a megaphone. And this megaphone, which we'll call BombMQ, has no affiliation or association with ActiveMQ. It's just a funny name for this megaphone. It has some weird acoustic properties. So when you talk into this megaphone, things that come out won't necessarily come out in the same order you put them in. So you might say, cut the red wire, cut the blue wire, and then the diffuser would hear, cut the blue wire, cut the red wire. So this is not going to be a fun time. But let's imagine if we replace this megaphone with a different megaphone. We'll call this one BombFka. It has no relationship with Kafka. It's just another funny megaphone. But this megaphone has some guarantees about its acoustic properties. Things you say into this megaphone will come out in the same order. How remarkable. It also has, these messages are also not ephemeral. Once they're set into the megaphone, they're there forever. So this megaphone has a replay button. If the diffuser forgets some instructions or just wants to rehear them, they can press the replay button and go back and hear them. The diffuser could just get up and go to the bathroom, come back and pick up where they left off. So of course, this is going to make the diffuser's job a lot easier. But it gets better. If you have more than one BombFka megaphone, you can speak into one of the megaphones and have your messages come out of different megaphones and still be heard by the diffuser in the same order. So this is not only going to make it easier for the diffuser, it allows us to have multiple diffusers, maybe even multiple bombs. So we're increasing the scalability of our game. Now this is just a metaphor, so don't take this too far, but I do want you to keep this in mind as I talk about Kafka today, and I'll reference back to it. Before we go any further, if you're not familiar with me, my name's Joe Kutner. I go by Codefinger on the web. And you may not know me. You may have seen some of my books. I've written 2 on JRuby and 1 called The Healthy Programmer. I also work at Heroku, where I'm the JVM or Java platform owner. Heroku is a platform as a service. And we recently launched a product called Heroku Kafka, which is Kafka as a service, Kafka running in the cloud. So you can use Kafka with your applications without the operational burden. And it's actually based on our own internal use of Kafka. We have a lot of data. We host more than 5 million applications and handle about 8 billion requests per day. And those 8 billion requests generate a lot of events, and all of those events get funneled into Kafka. So we built some infrastructure around making Kafka easier to use, and we wanted to provide that same experience to our customers. So I'll talk more about Heroku Kafka and how we use Kafka later on. But I'm going to start with an overview of what Kafka is and what problems it solves. Then I'll talk about how to use Kafka from Java, how to use Kafka with Spring. We'll take a look at an example application that calculates metrics using Kafka. And then we'll talk about Heroku Kafka. So what is Kafka? When I was first learning about Kafka, I was confused about where it fit into the ecosystem. So I went to kafka.apache.org and I read that Kafka is a distributed, partitioned, replicated commit log service. It provides the functionality of a messaging system, but with a unique design. And this left me kind of confused. This did not help. This is a very accurate description of Kafka, but I think it requires a great deal of context to understand what all this means. Like these terms like partitioned, commit log, unique design, what is that? So I think what Kafka is can be distilled down to something much simpler. Kafka is a distributed, publish-subscribe messaging system with guarantees around speed, scalability, and durability. Now these are terms you might use to describe a message queue, but Kafka is not a queue. It is a messaging system, but it uses a unique design to achieve higher levels of performance and scalability. Kafka can handle hundreds of thousands to millions of messages a second on a small cluster. So if you're comparing this to something like ActiveMQ, you're probably talking about thousands to maybe tens of thousands of messages a second. So Kafka is not a smidge better, it's like orders of magnitude better. So it achieves these higher levels of performance with its unique design. And in order to describe that unique design, we have to have a common vocabulary. So many of the terms that you may be familiar with if you've done any pub sub work are the same in Kafka, but they have a slightly different meaning or implication. So we'll start with producers and consumers. This is largely what you would expect if you've done any pub sub work. Producers create messages, consumers receive them. The difference in Kafka is the contract between the clients, the producers and consumers, and the cluster. So the Kafka cluster is a number of brokers, many different brokers, and the clients do not connect to individual brokers and then fail over. They actually connect to a seed broker which distributes their connection across the cluster. So they're really connected to all of the brokers. They are connected to the cluster, truly. The consumers also have a synchronous connection so that they are not just asynchronously receiving messages and going and doing things. The cluster is actually aware of the consumers. They even have a heartbeat. But at the end of the day, the producers are sending messages and the consumers are receiving them. The messages themselves are very simply just byte arrays. They have a little bit of structure, a header with some metadata, a key which can be used for routing, and a value, which is sort of like the body of the message. The messages are fed into topics, and topics are conceptually the same as what you would have in a message queue. They're like a mailbox where you put messages, and then consumers receive messages out of certain mailboxes. What's unique in Kafka is that topics are partitioned, and then the partitions of the topic are spread across the brokers in the cluster. So a topic truly exists throughout the cluster, not just on an individual broker. Each of these topic partitions is an ordered log of immutable messages. And this is probably the most important characteristic of Kafka. So let's break this down. It is ordered, which means not only that the producers will send messages and they will be stored in order, but that the consumers are guaranteed to receive their messages in order. So much like the Bamfka megaphone. It is a log. It's actually written to disk. So when a message enters the Kafka system, it's stored and it's there as long as you have your retention period configured. And it's immutable. So the consumers can actually go back in time and get messages from the past, replay them. That's particularly important for like analytic systems that want to recalculate things. So given that each of these partitions is an ordered log, each consumer has an offset. And that offset tells the cluster where that consumer is in reading from that partition. So this offset is what allows a consumer of Kafka to shut down, restart, crash, and then start back up again and pick up where it left off. It also allows consumers to seek to a particular point in the partition or just to go back in time and replay all the events. The consumers themselves are organized into consumer groups. And at a high level, these consumer groups are analogous to individual consumers in a traditional message queue. So you might have multiple consumer groups subscribed to the same topic. And then both of those consumer groups are guaranteed to receive each message from that topic at least once. But within the consumer groups, you have individual consumers. And these individual consumers do not receive every message from the topic. The individual consumers are actually assigned a partition or partitions by the cluster, and then they receive messages only from those partitions. So the partitions allow the cluster to scale, but also the consumer groups to scale. So you can scale two consumer groups independently. For example, if you have consumer group A and consumer group B both listening to the same topic, one might be archiving data, which is not like a time-sensitive operation. So you can scale that down. If it falls behind, it'll catch up at night when the traffic is lower. Consumer group B might be doing some kind of time-sensitive notification, so we want to scale that up so that it's always going to be caught up. So all of this, all these components create three essential guarantees about Kafka. Messages will be produced in order and written to disk in order. Messages will be consumed in order. And then topics will be distributed and replicated. So the topic partitions are distributed across the cluster. They're also replicated such that if you have a number of brokers go down, you won't lose any data. All right, so let's talk about how to use Kafka from Java. So Kafka is a JVM technology, so we're very fortunate in the Java ecosystem to have the Java client libraries for Kafka be maintained by the Kafka core team. It's actually, the client libraries are actually in the same Git repository as Kafka itself. The disadvantage is they're kind of low level. Like they require the use of Java concurrency APIs. They're not like very cloud native. For certain things, they require files on the file system. A little uncomfortable. But fortunately, we have frameworks like Spring and Akka that are building higher level frameworks on top of these lower level APIs to make it more comfortable to use Kafka. So I'm going to talk about both the lower level API and how you use it from Spring. So the Kafka Java client library for producers requires that you create a producer object, which you instantiate with a Java util properties object. That properties object is used to configure the producer, and at a minimum it must have 3 properties. The bootstrap servers, these are the seed brokers that distribute your connection across all of the brokers in the cluster. And then a key and value serializer. So remember that messages are byte arrays, so our clients are going to do the serialization and deserialization. So we tell the producer how we want to serialize our messages. So my messages will be strings, so I'll use the Kafka provided string serializer both for the key and the value. Once I have the producer, I create a producer record for my message. The producer record represents both the message I want to send and its destination. So I have message 1, which is some string message, and then my topic is where I want to send that message. I then pass that producer record to the producer.send method, which will send it to the Kafka cluster. And I do it again, and I do it again, and I do it again. What's important about this send method is that it's not a synchronous operation. It does not hit the wire when I invoke send. The Kafka producer actually in a background thread will queue up each of the messages I send and then send them to the brokers in batches. And it'll actually send them in batches based on their destination, and their destination will be determined by what message it is, what type of message this is, what topic it's going to. That'll determine where it's going, and then the Kafka producer will send them as efficiently as possible. So for that reason, the producer send method does not return like an immediate result. It returns a Java future. So if you care about what it's doing or what its result was, you have to call .get and then do concurrency API stuff. The consumer API looks pretty similar. You create a Kafka consumer and you pass it a properties object with the bootstrap servers again, and then this time a key and value deserializer, so the inverse of the serializer. Once you have the consumer object, you call consumer.subscribe and give it a topic or list of topics. And then you invoke consumer.poll, which is a blocking operation. That's why we're passing it a timeout. And this returns a list of consumer records. These consumer records represent messages and some metadata about the messages, like where they came from. Because poll is a blocking operation, you typically put this in some kind of loop with a control variable. In this case, running is an atomic Boolean, so I have to control that outside of the thread of execution. So again, I have to use my concurrency APIs. Poll is actually doing a lot more than just receiving messages, though. The first time you invoke consumer.poll, it locates the group coordinator for the cluster and joins this consumer to its consumer group. The cluster then assigns my consumer a partition or set of partitions and then rebalances all the partition assignments for that consumer group. It also establishes the heartbeat from the consumer to the cluster, so the cluster knows that this is online and working. And then finally, after it receives messages, it automatically updates the consumer offset, which is stored on the cluster. We can also do manual offset committing if you want to, for example, guarantee that your messages were actually processed before the offset is updated. Basically the same idea here. You just call consumer.commit sync after processing your messages. It's important to note that the Kafka consumer is not thread safe. By design, you should have one consumer per thread, which again means you're going to use concurrency APIs, probably executor service to spawn off threads for each of your consumers. Some of the more advanced usage of the API allows you to do per message offset committing. You can also manually assign partitions to consumers. You can store offsets outside of Kafka. And then in the most recent release of the Kafka client, they introduced Kafka Streams, which allows you to do single message processing as opposed to micro batches, which is the poll method. That's particularly useful for systems that are like piping data into, from Kafka into other systems. All right, so that is the overview of the Java API. Fortunately, Spring has introduced Spring Kafka, which makes it a lot more comfortable to use the Kafka client. At a high level, you use this enable Kafka annotation on your Spring Boot app. You then create a Kafka template bean, and you provide it with a map of properties. But those properties are just identical to the Java util properties we saw earlier. That Kafka template represents your interface into the Kafka cluster. So you wire it up to some other component and then call template send. So not terribly different from the producer API. The consumer API is where it really starts to get a lot better. So the Kafka Consumer introduces this Kafka Listener annotation. And you can apply this annotation to a method to effectively make it like a callback for the Kafka Consumer. So the Spring Kafka Consumer is going to handle the subscription, the poll, the looping around the poll method, and all of that stuff. And then it'll just invoke our callbacks when it receives messages. So greatly just reducing the amount of concurrency stuff we have to do. The listener annotation is pretty robust. It has allows you to set attributes for different types of configuration, like assigning specific partitions to this method. Okay, so let's take a look at an example application and see how this all comes together. So this example application I've created is a metrics calculation app. So it takes a primary application, which is like just your web app that receives web requests, and it calculates metrics for that app, things like response time based on the route that's requested, by looking at the application's logs. So of course, when calculating metrics for an app, you want to do that without influencing the performance of the application. So getting that from logging data is pretty ideal. So at a high level, it looks like this. You have your primary app receiving web requests. Each web request should generate a log, a router log with the path of the request and the response time, status code, things like that. We'll funnel those logs into our metrics app, which will use Kafka, and then roll up our metrics calculations and store them in some other persistent storage. At a lower level, the primary application is probably like a Spring app, just receiving web requests, just standard Spring or Spring Boot. If it's running on Heroku, we have this feature called log drains, which allows you to consume your logs over HTTP. So you can register a callback URL with the application, and then Heroku will invoke that with a post request for each logging statement. It looks like this. You run Heroku drains add, and then you provide it the logging endpoint for our metrics app. Each time the primary application receives a request, it'll send as a post request to this metrics endpoint a string that is in syslog formatted format, and it contains a whole bunch of data about the request. But what we're interested in is the path, what the path that was requested was, the service response time, and then the status code of that response. The metrics app's endpoint is actually just a very simple Spring Boot app that's also a Kafka producer. So this app has a single entry point called logs that receives a string body. The string body is the syslog formatted string that I showed earlier. It first has to massage that because, of course, all standards are not the same in every place. So the way that Heroku uses it is the way that is a little bit different than other places. So once we massage that string, we can actually use a class that's a part of Spring called RFC6587 syslog deserializer. If you have any questions about what this class does, God help you. It knows how to speak the language of syslog. It knows how to parse and deserialize, and ultimately turn that syslog record into a map. We'll turn that map into a string, and then that string into a JSON object, and then, or I'm sorry, the reverse. We'll turn that map into a JSON object, and then that JSON into a string. And then finally, we send that string to Kafka, to our Kafka template. I probably could have just taken these 5 lines and built them into like my own serializer instead of using the string serializer, but it's 5 lines of code, so I just wanted to leave it here. All right, so once that, or for each of those requests that the metrics app receives, it's going to put them into Kafka, and Kafka is sort of a standard off-the-shelf piece of the infrastructure. I'm, of course, running it on Heroku. If you've ever tried setting up Kafka, you may know that it's like a day and a half process. But on Heroku, it's just a single command. You run Heroku add-ons create, and this will attach, it'll provision a Kafka cluster, including Zookeeper and everything that it needs to operate. It takes about 1 minute to provision, and then it'll be attached to your application, and you'll be provided with the seed broker URLs. After you've done that, you install the Heroku Kafka client tools, which allow you to run Heroku Kafka creates to create a new topic. So in development, you're probably creating topics on the fly, but in production, you want them to be more like static things. So I've created a Heroku or a logs topic, and this is where I'm sending those logging statements that my producer receives. The client tools also allow you to inspect the Kafka cluster, find out what version is running, how many consumers are operating. You can also use it to get specific information on a topic. For example, you can see that the default number of partitions is 32, and the retention period is 24 hours. All right, so on the other side of Kafka, I have a consumer, which is my metrics aggregator. And this is just a simple Java process. So I'm not using Spring for this because it doesn't have any like web component. I didn't want the overhead of Spring. But unfortunately, that meant I had to use the lower level Kafka APIs. Unfortunately. So this consumer, it's a simple Java process. It's actually a single class with a main method. When it's instantiated, it creates a pool of connections to Redis, which is where I'm going to store my metrics rollups. And then in the start method, it fires off a new thread for each of my consumers. Again, I have to have that for thread safety. Each of those threads is going to launch with the loop method, which is pretty similar to what I showed earlier for the Kafka client. I'll subscribe it to my topic, then I'll invoke poll inside of this loop with the control variable. But what's going to happen each time I receive some messages, I'm going to convert those messages into route objects. This is just a very simple POJO that I created to represent each of those syslog records. And then I'll pass it to the receive method. So I'm kind of mimicking the Kafka Listener pattern here. And that receive method is largely just interfacing with Redis. So it's going to recalculate an average response time for the route of that request each time it receives a new request using those response times in the syslog format. So once all of my metrics data is in Redis, I can then consume it from anywhere. I could potentially have a view in my primary application that displays current response times, current metrics, or I might have some other admin interface. But the idea is Redis is really good at providing this kind of information to my other apps. It's not good at dealing with millions of messages a second. So Kafka is the system for that. I can also reuse my Kafka feed. So I'm putting these syslog statements into Kafka, and they're not useful only for calculating metrics. So in my sample application, I also have another consumer called the replay consumer. This consumer can be scaled up to take each of those log statements and then replay the request against a staging application. So in this way, I could test my staging application with real production requests without having any effect on the production application. So that could be another potentially useful pattern.
So those sequential messages that got written to a topic end up in Redis? That's where they end up?
Yeah, so each of the logging statements goes through Kafka, and then the consumer, for each time it receives a new one, updates the rollups or the averages that are calculated and stored in Redis. So yeah, so Redis is the place where we're going to. I'm using Redis because it's very good at like incrementing a value and then calculating a sum or an average based on the sum and the count and all that. All right, so the code for this application is on GitHub. If you are not interested in the application itself, you still might be interested in how I've got it set up with Docker. So it's all prepared with Docker Compose to stand up Kafka and Zookeeper, even Redis. When you run Docker Compose up web, it'll launch the metrics app. So metrics calculations are one great use case for Kafka, but there are plenty of other. The most commonly talked about is user activity. Of course, Kafka was created at LinkedIn, where folks were tracking every user action in an application, whether it's like clicking on a link, viewing an ad, updating your profile, and then feeding that into Kafka. And on the other side, different parts of the organization can then use that feed for targeting ads or potentially suggesting people that you should connect to. String processing is another common pattern. You might have multiple feeds coming into Kafka, and then you're using Kafka to funnel all of that data into your analytics systems. So at Heroku, we're using Kafka for calculating metrics, not only our own internal metrics, but also the metrics for our customer applications. So this is actually very similar to the demo app I just showed. If you have an app running on Heroku and you go to dashboard.heroku.com, you'll see a bunch of graphs for like response time of your application, throughput of your application, the CPU load, all that kind of thing. All of that data comes out of your app's runtime, and we feed it into Kafka. And then on the other side, we have a consumer that's rolling it up and storing the data for these graphs at a 1-second interval in Postgres. So again, Postgres is good at storing the 1-second level data for the graph. It's not good at millions of messages a second. We're also using Kafka for our Heroku API event bus. So the Heroku API is like the hub of Heroku's internal infrastructure. Everything you do on Heroku, creating an app, deploying, changing your password, goes through the Heroku API at some point. So for each of those actions, we generate an event, funnel that into Kafka, and then different parts of our organization can consume that for different purposes. Our build team might be watching for increased rate of failure of people building apps. Our production runtime team might be watching for outages and things like that. Yeah, so it's the same feed going to different organizations, which are then doing many different kinds of things. Some might be feeding it, for example, we have into a metric system that's stored in Postgres. Someone else might be sending out notifications. So what the consumers do is completely independent of the feed itself, and that's what Kafka provides, is this ability to have a single source of these messages and then consume them from many different consumers and not overwhelm the cluster. And of course, we have a Heroku Kafka product. You can learn more about it at heroku.com/Kafka. It could not be any easier to create a Kafka cluster. So check that out. You're also welcome to stop by the booth. We have a booth in the community hub. If you have any questions about Heroku or Kafka, please come and chat with us. Thank you.